Alright, so today we're going to understand the gravity of the subject, which is the subject, gravity, in Chapter 7, also satellites and projectile motion and how that all came about. To do that, we're going to talk about our old friend Isaac Newton, Sir Isaac Newton, yes, the same Newton who gave us the three laws of motion. Alright, but he also gave us a lot of understanding about the law of gravity. We say he discovered gravity, but he didn't actually discover it. It was right there. He explained gravity, would be a better way to put it. And according to legend, he was sitting under a tree at his home, which was a farm kind of area out in the rural area, and he got bonked on the head by an apple. In fact, was home from Cambridge where he was going to college because there had been, I don't think it was the plague, but it was an outbreak of some kind of deadly disease at that time. And so they just sent everybody home, hopefully to reduce the rate of everybody getting infected. But anyway, he was sitting on the tree and an apple hit him on the head. Now, if it happened exactly like that or not, we don't know. But we do know he was thinking about the apple falling. And also, probably not as famous and well known, but the moon. He was thinking about the moon. And the moon, according to Newton's first law, if it had forward motions, obviously it was moving, okay, it should continue to move in a straight line according to Newton's first law, which says that objects in motion stay in motion at a constant velocity, same speed, same direction, unless a force acts on it. And so what Newton was wondering was, what if the moon was being affected by the same force that caused the apple to fall down and hit him? Okay, for example, the inertia of the moon, if it's moving this direction, should just continue to move that direction in a straight line. But Newton said, what if the Earth were exerting a force on it, like this direction? And because of this force, it ends up going in between these two forces. The net force ends up being somewhere in between, which causes it to be a curved line because you have the inertia wanting to pull it this way based on its velocity and mass, or based on its mass, but because it's got a force and velocity in this direction. And if the Earth's pulling on it this direction, that will give us this curve thing, which would result in it going around the Earth. In fact, here's one of Newton's first drawings of what he hypothesized what might be happening, something like this, and how things might circle around the Earth like the moon does. All right. And so, at any rate, this is his idea. And so basically, he was saying the same thing as force is acting on this apple, which is being pulled toward the Earth. And the moon is also being pulled toward the Earth, but since it has a horizontal velocity or a velocity away from, at a tangent from the Earth, then it's going to go somewhere in between, which ends up in a curved path, which causes it to circle. So in a sense, the apple is falling to the Earth. The moon has too much velocity to fall to the Earth, but it's falling around the Earth. And so it continues to fall around the Earth because even if it's over here, the Earth still pulls it this direction, the velocity still pulls it out that direction, inertia causes it to want to go this direction. And so it just continues to go in this curved path around the Earth. These observations that Newton made led him to come up with what we now know are called the law of universal gravitation, or otherwise known as the law of gravity. We usually just shorten that. And basically what he said was that every object that has mass, which is everything because all matter has mass, exerts a force on every other object that has mass. So in other words, any two objects that have mass will have a force of gravity. And here's the formula he came up with is Fg, which is force of gravity, is proportional to the mass of one object times the mass of the second object, the two objects that have mass, divided by the distance squared. And basically this says any two objects that have mass have an attraction. That means if I'm sitting at my desk has mass, I have mass. There's an attraction between me, a gravitational pull. If someone says, I don't feel that pull, I don't feel attracted to my chair or the floor or the wall or whatever. Why do I not feel that? And the answer to that is gravity is a very, very weak force. Okay? If we compare it to electricity, or even magnetic forces, and certainly the nuclear forces that hold the atom together, the nucleus of the atom together, gravity is very, very weak. So it says, well, but if I jump off the roof, it's a very strong force. It slams me down to the ground, breaks my bones, could kill me. And that's true. Okay? But the reason there's a force is because the mass of one object, which is the Earth, is humongous. And since it's so large, we can feel the force that it exerts on us. technically you exert a force on the Earth, but because its mass is so large, it is not affected a great deal by the force that you put on it. Okay, you put an equal force on the Earth, but since it has such a big mass, you're not going to see the Earth change its path or anything because of your force. But you are exerting a force on it, just like it's exerting a force on you. All right. And so, like I said, basically it's only felt because the Earth is so large. If you're not near something large like a planet, then you're not going to feel the force of gravity. The sun just gives you an idea of how humongous the sun must be and massive in order to keep all the planets going, pulling and going around it. The moon has gravity, but it's much less, about a sixth of the Earth's, and so you would feel a lot less force of gravity or weight if you went to the moon. We say you are weightless. You're not weightless, but you notice they bounce around on the moon because they only weigh about 1/6 as much as they do on Earth. So that's basically it. So if you want to have more gravity, basically you have to change the mass of the two objects. If you went to a bigger planet like Jupiter, then the mass would be enormously greater and you would be much heavier, and maybe even to the point that it would squish you. But at any rate, that increases. As you increase the mass of one or both objects, that's going to increase the force of gravity because that's on top of the fraction. Distance, on the other hand, is going to decrease. The farther apart the two objects get, then the less gravity you will feel between them. Okay? And so we talk sometimes about leaving the Earth and leaving its gravity as a rocket ship goes off. Technically, that is not true. You can't escape gravity. Okay? If I went throughout the universe, wherever I want to go with my spaceship, does my spaceship have mass? Yes, it does. Does the Earth have mass? Yes, it does. Is the distance big? Yes, it is. But is this value ever going to be zero? No. This number will get, as you get a big, big number and it gets squared and it gets really big, the denominator gets big, it's a lot bigger than this number. It makes a smaller, 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 smaller fraction, but it never goes to zero. So technically you can't escape the pull of the Earth's gravity, but you can get far enough away from the Earth that it reduces that gravity to such a small amount that you do not notice it. Okay, just like I don't notice the gravity between me and the desk because our masses are small, even though our distance is short. You can get such a far distance from the Earth that you don't feel the pull of the gravity of the Earth, but you haven't escaped it. There is still a pull; it's just getting smaller and smaller and smaller to the point that you do not notice it. Okay, so you could argue that your weight, if you have a weight problem, really what you have is a gravity problem or a density problem, a distance problem. If you could get far enough away from the Earth, you would weigh less. Now, something you have to keep in mind, it's not the distance to the surface of the Earth, it's to the center of the Earth. Now, for small objects like us, the distance between our feet, for example, and the center of our gravity is only about 3 or 4 feet, maybe. But the Earth has an enormous distance or diameter, okay? And so the distance from the Earth's surface to the core is 3,900, almost 4,000 miles, basically. Okay, 4,000 miles. So we're already 4,000 miles away from it. In order for us to double this distance, we would have to go basically 4,000 miles up into the air. Okay, just for a point of reference, Mount Everest, the highest point on the Earth, is, if in this picture, wouldn't even be much more than just a little bump there, because it's only 5.5 miles, and that's probably exaggerated even then. Okay, so it's only 5.5 miles. You'd have to go almost 4,000 more miles up in the air before you would be twice the distance. But if you did travel twice the distance, so it'd be 2d squared, the 2 would be squared also, so it would be 4 on the bottom. So you would actually, the force of gravity or your weight would be 1/4 what it is on the surface of the Earth. Okay, so as you get farther and farther out, then it's going to continue to be. If you went that much farther again, another 4,000 miles out into space, now you're 8,000 miles into space, it would be 3 times the distance, which squared would be 9, so you would weigh 1/9. Okay, if you went 4 times, which would be up off the screen up here somewhere. If you went the 4th time, then you would be 1/16 as much. And so not only does distance decrease your gravity, it exponentially. The bigger the number, the bigger the distance away, it decreases it. All right, and this is known as the inverse square law. All right, and we can demonstrate it right here. If we have if we have a light, okay, and as it's coming out here, the same amount of light is coming off of it, but as it gets farther and farther away, it's spreading out over a bigger area. And so you're actually getting less and less light as you get farther away because it's being spread out over a larger area. And that's kind of how we can think of gravity. Think of gravity as spreading out from the Earth. As we get farther away from it, the same amount of pull is being spread out over a bigger area. And that's basically called the inverse square law. Another way to look at that, think of it if you have a can of spray paint. Okay, as you spray the paint, if you're up close to an object, you get lots of paint. Unfortunately, it may run. As it gets the same amount of paint, it's spreading out over a bigger area. So if you're farther away from the object, it may get to the point where it's so thin that you're not putting enough paint on. And so you have to find this perfect area in between here where it's not so close that it runs, you get too much paint, but it's close enough that you still have a concentration of paint, but that will coat it good. And that's kind of basically what gravity does. It's inverse square law. As you get farther and farther away from the Earth, you get less and less gravity. And you can never escape the pull of the Earth, but you will get to where it's such a small amount that you do not notice it. Now, if you went to Mount Everest, which is 5.5 miles farther, so that'd be 3,964 miles above the Earth's surface. So if you take the regular Earth's surface, divide by the increased distance you are and square it, and then times your weight, that will tell you how much just traveling to the top of Mount Everest might reduce your weight. If you're lucky, it might come up to a pound. It might not. So it's to really lose weight by going farther away from the center of the Earth, you're going to have to go a really, really far distance. And the gravitational formula, we said that the force of gravity is proportional to the mass times one object times the mass of the other object divided by distance squared. But there's also a coefficient in there, something that relates it, kind of like a pi. If you look at pi on a circle, basically it says the diameter is always going to be, there's a certain relationship between the diameter of a circle and its circumference. The circumference is going to be the bigger number. It's always going to be 3.14, about 3 times bigger than the diameter. And that's just a relationship or a coefficient that ties those together. Okay. Well, the same thing is true of gravity. Okay. There is a coefficient that ties those values together. And so the actual formula for gravity is F, force of gravity, is equal to G, that's the coefficient, times mass 1 times mass 2 divided by P. Now, it turns out they want to figure out how can we figure out G. So what they did is they took a ball and they found the weight of it, or the mass of it, which is the pull of gravity on it. And then they rolled a big 6-ton metal ball underneath it. They knew how big it was. They knew how much it weighed, what the distance was to the middle. And so they could figure out the distance. They needed the mass of this object, the mass of this object. Now, since you had this massive object here, technically, that's more than the pull of just the Earth. Now there's the pull of this object, the 6-ton ball, and that. And they had to put a little more weight over it. It made it weigh just a little bit more. It wasn't much. And this had to be a massive 6-ton ball. But it did make this weigh a little more. So now they knew the mass. They could see how much the gravity, or the force of gravity, increased by how much mass they had to put on here to make it balance now. And so they knew the mass of the first object. They knew the mass of the second object. They knew the distance between them. And they knew the force, how much it increased the weight of the object. And so they could solve for this G. And when they solved for G, they found out that G is equal to 6.67 times 10 to the negative 11th newtons times meters squared divided by kilograms squared. Now, I wouldn't worry about the units at all. Just know that that will cancel everything out so that you end up with newtons for this. Okay, and I wouldn't really worry about this number. But the thing is, it's 10 to the negative 11th. All right. The point is, it's very, very small numbers. 0.1, 2, 3, 4, 5, 6, 7, 8, 9.